Continuing our previous discussion, here I have drawn a very simple example of a corner circuit model representation for the most general unitary operator acting on a qubit. Using the Z-Y decomposition, we found that it is possible to decompose the most general unitary as a sequence of 3 rotations around the Z and the Y and the Z axis respectively by certain angles. It is quite remarkable that in order to realize the most general unitary acting on the qubit, visualized as rotations around certain axes on the Bloch sphere, it is sufficient to do this rotation around a certain fixed axis, in this case only the Z and the Y axis. Finally, let me remark that in the corner circuit model, time goes from left to right. So here we have a qubit, the line, so this wire represents the qubit, and the qubit is normally assumed to be initialized in the 0 state unless otherwise specified, and the state is subject to certain gates and comes out from the right. So here, the operations done on this qubit, represented as these boxes, goes from left to right. So we have the rotation by the angle θ1, followed by a rotation of the angle θ2, and finally θ3. However, when we're writing down the operators in this way, because remembering that the cat or the state is being applied, the initial state is being applied over here on the right-hand side, so this order for these operators goes from right to left. Here we have the rotation of the angle θ1 acting on the initial state, followed by this rotation of θ2, and followed by the rotation of θ3. So these two orders are actually reversed. The last part of a quantum computation task is the measurement. In a corner circuit model representation, a measurement is shown as a box with the meter inside. For the case of a qubit, this measurement is done in a computational basis. And we always assume a projective measurement in a computational basis at the end. That is, this measurement can be expressed as 2 pi, 2 projective operator, where pi1 is given by the projector into the 0 state, and pi2 is given by the projector into the 1 state. So this could either be the end of a corner computation task, where we get the measurement results. So this measurement reveals 1 bit of information. We get to know either is 0 or 1. Or in a more complicated quantum computation task, the result of this measurement could be communicated to another part where, depending on which measurement result we got, further computation is carried out. Hence, sometimes you could see there are 2 extra lines at the end to emphasize that this measurement has 2 possible outcomes: the probability of getting the 0 that corresponds to the pi1, and the probability of getting 1 that corresponds to the pi2. It is important to emphasize that although 2 lines have been drawn to indicate that it is possible that the detector corresponding to this would click, or the detector corresponding to this would click. However, at any time, only one of the detector will click. So the maximum amount of information that we could get is only 1 bit. As an exercise, let's work out what will happen for this very simple quantum circuit computing model, where we have the state which is initialized in the 0 state. After that, it is being applied by an Hadamard gate, and then a measurement is carried out. So what will we predict? Well, we know that the action of the Hadamard gate acting on the 0 state is to turn this into a superposition of the 0s and the 1 state with the same probability amplitude 1 over square root of 2 for the 0 and 1 over square root of 2 for the 1. So the measurement will then give us the same probability for the 0 detector to click, that is probability half, and the same half for the probability that the detector corresponds to the 1 state will click. So these 2 measurement outcomes will show the same probability. This is similar to a perfect coin that is fairly tossed. Half of the time we will get a head, and half of the time we will get a tail. However, unlike a classical mixture, this is a Compton superposition of the 0 and 1, which is actually in another state. It's the diagonal state, or the plus state. This measurement Hadamard combined with the projective measurement in the computational basis can also be thought as performing a measurement in the plus-minus basis. When the zero state is measured in the plus-minus basis, we know that half of the time the plus state detector will click and half of the time the minus state detector will click. Hence, it is sufficient to assume that at the end of a corner circuit model, the measurement is always done in the computational basis. That is because in order to realize a measurement in any other basis, we could always have a unitary operator in front of the measurement. For example, over here, a Hadamard before the measurement is effectively doing a measurement in the plus-minus basis. As another example, let's apply a most general unitary for our initial state 0. And after that, let's apply an X gate and do a measurement. Let's find out what will happen. So we know that the most general U acting on the 0 could give us alpha 0 plus beta 1. And the X gate flipped the 0 and 1 state, so that will give us beta 0 plus alpha 1. The probability of getting the 0 is given by the absolute value of the beta squared, and the probability of 1 is given by the absolute value of the alpha squared. So these two probabilities add up to 1 as it should, because here the cat is properly normalized. Just as one more example, let's study another quantum circuit where the initial state, again I will assume it's initialized in the 0 state, is being applied by a general unitary and another Hadamard gate. After that, a measurement is carried out. What do we predict? Well, let's see. So after the action of the U, we have the alpha of 0 plus beta of 1. And the Hadamard turns the 0 into plus and the 1 into the minus. So here we will have alpha over square root of 2, 0 plus 1, that is the plus cat, plus beta over square root of 2, 0 minus 1, that's the minus cat. So the measurement for the probability that the 0 outcome is observed is given by the square of the probability amplitude in front of the 0 state. So that's alpha plus beta over square root of 2. So the square of that, or the absolute value squared, is alpha plus beta, absolute value squared over 2. For the other probability P1, that should be given by 1 minus of this, and it is given by the absolute squared of the coefficient in front of the 1 state. So here we have alpha over square root of 2 minus beta over square root of 2. Hence, we have the absolute value of alpha minus beta squared over 2. As a homework exercise, you should check and convince yourself that indeed these two probabilities add up to be 1, as it should, because we started with a normalized state. After going through unitaries, the state should remain normalized as it goes through this corner circuit. A final remark is in order. Here, I have assumed that the state is always initialized in the 0 state. However, if you would like to initialize the state in any other arbitrary state, for example, alpha 0 plus beta 1, you could always initialize the state as a 0 state and apply a unitary on that state. Hence, this combination of initializing the state in the 0 state plus the general unitary can be thought of as an preparation step where you could prepare any state in a superposition of alpha and beta. In fact, that is why sometimes you will see that this part of the corner circuit is ignored and the system just started with the state alpha 0 plus beta 1 at the very initial step. Finally, let me introduce this representation of a corner circuit model where you see a line, a slash on top of this wire. So remember the wire is representing a qubit for example, initialized in the 0 state. So this slash with the n simply means n qubit. So we prepared n qubits, each of them in the 0 state, in this product form, 0 tensor n. And similarly, the H tensor n means n Hadamard being applied on each of the qubit independently. So this is simply a shorthand notation for this circuit shown over here, where we have n wires, n lines, each of them representing a qubit initialized in 0, and each of them is being applied by the Hadamard. I would also like to introduce you to the so-called circuit identities that help us to simplify a quantum circuit by inspection. So, for example, it is a well-known circuit identity that a Hadamard followed by an X gate followed by another Hadamard is simply the Z gate. Such identities help us to identify certain parts of the quantum circuit that could be simplified. So rather than applying 3 quantum gates, it is equivalent to apply only a single quantum gate. You can easily verify this, perhaps by using the matrix representation of each of the operator, and by multiplying out the matrices, confirm that this is indeed true. However, let me use another method to show that this is true. One of the important properties of the Pauli operators is that when you take any 2 different Pauli operators out of the set x, y, and z, these 2 operators will anti-commute. For example, let me take the Pauli x and Pauli z operator. The anti-commute, that is to say x times z plus z times x, that is equal to 0. So we can move one of the term to the right side and apply a z operator on the right on both sides that give us xz squared. Z squared is the identity, so that's left with the x only on the left side, and on the right side we have minus zxz. So this is just a consequence of the fact that these 2 Pauli operators anti-commute, which is quite an important property of the Pauli operator. Equipped with this, we can show hxh is equivalent to z, so let's write it out. And let's remind ourselves that the Hadamard gate is the same as x plus z over root 2. So plug in here, we will have 1 over 2, and x plus z times x times another x plus z. So for the first part, we have x times x, that's the identity, z times x, followed by this term. Alright, so identity times the x, that's the x, identity times z, nothing happens. Here we have zx times x, so zx squared. X squared is the identity again. And here we encounter zxz, which is just the negative of x, as seen from this box. So here the x minus x cancels, we have 2z, and so divided by 2, we will have z at the end. So we have shown that hxh is equal to the z. Hence, I've verified this circuit identity over here. As another simple exercise, let's find out what happens if I have a Hadamard followed by a Z gate followed by another Hadamard gate. Repeating this calculation, you can see that this is just equivalent to an X gate. As an exercise, I invite you to try, what if you have a Hadamard followed by the Y gate and followed by the Hadamard? And if you have a Hadamard followed by the T gate, the pi over 8 phase gate, and another Hadamard gate, this is equivalent to which gate? As a final application of this important anti-commutation relation between the Pauli operators, let us use these results to verify this circuit identity. That is, a rotation around the x-axis by an angle theta sandwiched between 2 z gates is equivalent to just a rotation around the x-axis by an angle minus theta. Let's see. So we have z, rotation around the x-axis by an angle theta followed by another z. We remind ourselves that the rotation around the x-axis with the angle theta as simply e to the power of minus I theta over 2 times the operator x, and that is cosine of theta over 2, the identity, minus I sine theta over 2 of the x operator, and another z operator behind. So for these two terms, the first term we have z identity z, so that is just simply z squared, which is still the identity, so we have cosine of theta over 2 of the identity. For the other term, we have z xz, so we recognize that z xz is simply minus x, so this will turn this minus into a plus, so that gives us I sine theta over 2x, which is simply rotation around the x-axis but by an angle minus theta. In summary, we have studied in quite some detail of the corner circuit of a single qubit. We shall now move on to study multi-qubit gates and their circuit representations, which are more interesting.